Okay, so I want to quickly finish what I wanted to do last week, which is the deterministic parts, the deterministic parts of open games. So in particular, the other composition operator, which is the monoidal or tensor product. And that completes the graphical language and lets us draw these circuit diagrams for open games as long as the strategies are pure. And we could do just as much work as before with the other operator and then even more in-depth examples for how they interact. But then we'll be here for weeks and weeks and weeks, and I don't have time. So I'm going to hand-wave that and then move on as quickly as I can to Bayesian stuff in order that I didn't waste my time introducing the probability a few weeks ago. So to remind you, a generic open game G from x plus x minus to y plus y minus consists of three pieces of data, a set called sigma g, the strategy profiles, a function, which I'll write g blank, from sigma g to the lenses from x plus x minus to y plus y minus, which is to say pairs of functions x plus to y plus and x plus times y minus to x minus, and then a relation telling you when an element of sigma is an equilibrium given a context, and the context consists of a lens like this, and it turns out that one of these is just an element of x plus in disguise, and a lens like this, and it turns out that a lens like this is just a function from y plus times from y plus to y minus in disguise. And then last week we went through the sequential composition of these things in all of the gory detail. Okay, for the other composition operator, let's suppose we have another one. So all of these now have ones, and then we have another one from x2 plus, x2 minus, y2 plus, y2 minus, and it's given by the same data. And then we want to compose these in parallel. So we want to, given this, we want, and the diagram actually looks like this. It looks like just these drawn next to each other with no joining of wires. But the result, which I want to call sigma, G tensor H, is going to so on the objects, this tensor product is going to be the same as it was on lenses, which is to say monoidal product on the top and bottom. So x1 plus times x2 plus. On the bottom I'll reverse it because I think that's the convention I was using. So x2 minus times x1 minus. Y2 minus times y1 minus. So given this data for two of these, I want to define this thing. So first thing is, what is the sigma of it, the set of strategy profiles, and just like before, I just have to tell you that this composes by Cartesian product. So a strategy profile of this thing consists of a strategy profile for this thing and a strategy profile for this thing. And the reasoning is exactly the same as it was last week, which is that we really take a disjoint union of all of the decisions that are made in these two components. The Second thing, now if you remember, we had a tensor product operation on lenses, which is actually very obvious. That's just running the top function and the bottom function, running the top functions in parallel, running the bottom functions in parallel. That's, you just look at it and there's only one thing to do. So, in order to, given an element of this, which is some sigma tau pair, we want to get a lens in this, a lens of this type, and we can get this by taking the lens from G given sigma and the lens of H given tau, and then we can take their tensor product as lenses. So basically all of the hard work to do that was done 2 weeks ago. Now, for the sequential composition, all of the hard work was involved in defining the E relation of the composite, and here it's exactly the same, but I want to do it in much less detail. Basically, it feels the same kind of thing, that we take this, we take a context for the composite, and we're also given a strategy profile for each of the two components, and then we want to kind of project that, like specialize that context to the point of view of one component. So it's exactly the same idea as for sequential composition, just the details are different. So, so we want to define E of G tensor H. So this needs to be a subset of this times the set of contexts for this composite, which is 1, 1, x, 1 plus times 2 plus x2 minus times x1 minus, and then y1 plus times y2 plus y2 minus times y1 minus 1, 1. So, just like usual, a context for this thing consists of an element of the forwards thing here. That's this. So this thing is really the set x1 plus times x2 plus. So this thing is a set of pairs. But this thing makes our life difficult, because this thing is a function from the forwards things on the right to the backwards things on the right. So this thing is a function y1 times, oh no, this thing is the set of all functions from y1 plus times y2 plus to y2 minus times y1 minus. Okay. So this one makes our life easy, because this is just a set of pairs, so we can just project out each one. This one makes our life difficult because we can't just immediately project out one of the two sides. So, as before, we want to define E of G tensor H to be the set of sigma tau hk such that sigma is an equilibrium of, switching notation as usual, sigma something is an equilibrium of G, and tau something is an equilibrium of H, where here we need to have a context of G, which we're going to get from HK, and we're going to use tau to get it. And then here we have a context of H, which we're going to get from HK. Again, I'm using capital H and small h, they're not related. and we're going to use sigma to get that. So it's, again, the same idea as last week. We get this cross influence of sigma and tau, which is Nash-like. And, okay, in this case, it's actually, for now, going to be easier because I want to go through this quickly rather than trying to give a kind of deeper understanding. So I'm going to use these forms rather than writing it in terms of lenses. These forms are kind of the quick and easy one. So we need to give a HK pair for G, and, well, our H here actually has the form, because H is an element of this Cartesian product, so this H actually consists of a pair H1, H2. And, of course, I'm implicitly applying this isomorphism. And so we can just project out and say H1 is the history which is in G's part of the context. And similarly, H2 here. Now, for the other ones, you have to do some manual work. So I'm going to provisionally call this K1. So K1, I need to give some function from y1 plus to y1 minus. So this is going to be the continuation from G's point of view. And how are we going to get this? Well, we know a strategy profile for H, namely tau. So we know how H plays. And we also know the history for H, which is small h2. So what we actually want to do, so in order to define K1 of some element of Y1, well, ultimately we have to apply, we have our function K. So K is a function from Y1 plus times Y2 plus to Y2 minus times Y1 minus. So ultimately we want to apply K of something and then take, if we take its second output, then we get an element of Y1 minus, which is what we want. And okay, so for this we need a Y1 plus and a Y2 plus. Well, we have a Y1 plus. That's that. Now, we need a Y2 plus. So Y2 plus is going to be the output, the play made by H. So, in order to do this, what we need to do is, well, we need to take, if we apply the strategy profile tau to H, this gives us a lens from x2 plus x2 minus to y2 plus y2 minus. And now if we take, and remember the lens is a pair of functions, so if we then take the forwards part of that, which long ago I gave this notation superscript plus, that's a function from x2 plus to y2 plus, okay? So if only we had an x2 plus, this would give us a y2 plus. But we have an x2 plus, it is h2. And this is the formula for this. So this thing defines a function from y1 plus to y1 minus using the other data that we have available to us. And then if we plug this in here, this is the context which G sees. And then we can symmetrically So you can also overkill this and write this purely in terms of lenses. But like I said, I'm doing this quick and dirty just to give the definition. So we also need a function from y2 plus to y2 minus. So this is basically symmetric. No. All the reasoning is the same but reversed. Okay. Now, this completes the definition of this tensor product. Then you have to do some horrible, boring stuff, and actually quite a lot of horrible, boring stuff. And you can prove that this thing actually satisfies the properties of being a monoidal product. It defines a monoidal category. So you need to prove a bunch of conditions, including the fact that this and the sequential composition from last week distribute over each other. So that if you have four things like this, and if you read it this way then this way, or this way then this way, you get the same thing. G1, G2, H1, H2, that G1, G2, tensor, H1, H2 equals G1, tensor, H1, G2, tensor, H2. And you can imagine just how unpleasant this is. But fortunately, it's true. So the methodology is that I suffer once for 20 pages or so. And then after that, we know that these circuit diagrams are completely valid, everything just works, and then we can just draw circuit diagrams forever, and we know that nothing will go wrong. Okay, now there's also you also need to check that this does the right thing game theoretically. Okay, so now we have a full complement of composition operators, sequential and parallel. You can also define more, but this is a sweet spot which corresponds very nicely to the diagrams we can draw. And in terms of these two, we can now give a generating family of open games which generates basically all of the extensive form games, give or take some details. The two generating families are, one is called a decision, subscripted by a pair of finite sets, which is an open game from x1 to y reals, and this subsumes the thing that last week were player 1 and player 2. So this is given by, the strategies are the functions from x to y. These are the pure, so this is going to represent, I should say, a decision of a player who is choosing a y given an observation of an x. So this is the set of pure strategies available. The lens that you get, the set of these things turns out to be in bijection with the set of these things anyway, because the backwards function goes into 1, so it disappears. So the play d of that, d of some f implements this bijection. And then the third thing is that the equilibria of, so when is some f an equilibrium given a context consisting of a history which is an element of x and a k which is a function from y to the reals? Well, precisely when when f of h, so in situation H, f plays an argmax of k. So f of h is in argmax of k. Okay, so this defines, and okay, you can make this definition for any set x and y. You can restrict to finite sets if you prefer. So we consider that to be one generating family. And then the other thing that we can make is that for any lens from, if we have a lens from x plus x minus to y plus y minus, x minus to y plus y minus, we can upgrade this lens to an open game. So these will be called a zero-player open game. These are one-player open games. These are zero-player open games. These are our two generating families. And these are given by, so we need to add the extra data. So sigma is going to be a one-element set, just a point. And I'm abusing notation now, so I'm considering lambda to be both the lens and its upgraded version as an open game. So it says that playing the one strategy profile we have just does the thing that we have. And then the equilibria are going to be always true. So this thing never fails to be in equilibrium for the reasons I was saying last week. Okay, now we have two generating families, and we have two composition operators. So the things that you can generate are precisely in correspondence with the things that you can draw as diagrams, with these as diagram elements. So, so we get this correspondence between the things that we can draw, and so if I say some technicalities, we get a subcategory of open games. We get the subcategory generated by these two things, and that corresponds to precisely the things denoted by the diagrams that we can draw. And that's the setting that we do game theory in. So then, for example, it turns out that one of the things you can check is, so if you take these decisions specialized to x being the one element set, so these are now decisions making no observation. So now I'll draw these as triangles like this. So remember, we have a one element set coming in. If we have a finite list of sets, we can dyn, yn. So we just take a bunch of these, put them in parallel with each other using this tensor operator. Then we do a bunch of unpleasant calculation, and what we find is that the equilibria of this d1, dn, so this is some finite tensor product of decisions, given, so the strategy profiles of this are so the set of strategy profiles of this is y1, because it's the functions from the one element set to y1. So this lives in the tensor product of all these y's. And then we need an element of, so our h goes away, it's just an element of 1. And then we have a k. And this is a function from the product of the yi's to Rn, where n is the number of sets that we have. And it turns out you can calculate that this relation captures, so this holds if and only if this thing is a pure strategy Nash equilibrium of the game whose payoff function is this. Okay, so if and only if is a Nash equilibrium of, and I'm going to write K, but really I mean the normal form game whose payoff function is K. Okay. So again, this is a deeply unpleasant proof by induction. Okay. And then you can start combining these things. So you can start drawing circuit diagrams that look like the thing that you want them to be. For example, I can say, here is player 1, so I call this D sub 1x. I'm going to copy. Remember, I already introduced some special diagram elements for lenses, so I'm going to continue using those for these. So our diagram language actually is extending the one that we already had for lenses. So every diagram of lenses is still a valid diagram of open games by being one of these. So we have a player choosing an X, and then we copy it, and then in parallel we have two players. So a player choosing a Z given a Y, choosing a Y given a Z, and a player choosing a Y given an X, and a player choosing a Z given an X. So this is one player sequentially followed by two players in parallel. And then some payoff function. This is reals, reals, reals. So this thing is coming from some function from x times y times z to r cubed. We can carve up this diagram with cuts, and then we can build the resulting game from our generators using these two composition operators, and at the end, it does the right thing. So if we call the resulting game G, the set of strategy profiles for this turns out to be exactly the pure strategy profiles for the game that we want. Namely, player 1 can just choose an X, player 2 can choose a Y given an X, and player 3 can choose a Z given an X. And then the equilibria of G. So strategy profile is some sigma f G. Let's call this x, some x f G. And then, because this diagram has no dangling wires, the contexts go away, so this becomes star, star. So we have an element of 1 and a function from 1 to 1. They go away. And then, if we unroll everything, this turns out to be equivalent to 3 conditions, which are precisely the equilibrium conditions for this game. So it says that x is in the argmax over all possible x primes of player 1's payoff if they played x prime. So player 2 and player 3 strategy follow the x prime that they would play, then they get their payoff. The equilibrium condition for player 2 is that f of x is in the argmax of all the y primes over x y prime g of x second component. So crucially, this is Nash. This is not subgame perfect. So this is this is only required to hold in the situation where player 1 did actually play X. So if this was subgame perfect equilibrium, then this condition would need to be strengthened to holding for all X prime. I could say a lot more about this, but I won't. And then the third condition is symmetric. So g of x is in the argmax of z primes of u, third component of x, f of x, z prime. Okay. So we can continue to do examples like this. We can draw circuit diagrams for games, either by hand, or if you're sensible, you use a computer. You can derive these conditions, and these in every case you get what falls out from the definitions is precisely the equilibrium conditions of the game that you wanted to draw. So this is the meta point, which can't exactly be stated as a theorem, which is that these circuit diagrams look like the right thing. This is a intuitive language for the information flow in this game. Okay. I'm sorry I'm having to go very quickly. I want to move on to talking about probability. So the big problem that we have for probability is that lenses don't work as we've defined them. So on a technical level, in order to define lenses as I've defined them, what you actually need is a Cartesian product on your starting category. But I've written this in terms of sets, so this is the Cartesian product. What this means is that we can copy, but not just that, but we have this magical property that if we copy an input, if we do a function and then copy its output, it's the same thing as copying its input and then applying the function to both copies in parallel. And it turns out that so in the category of stochastic processes, you still have this ability to copy, but this property of copying commuting with everything no longer holds. This is false. And what that means is that if you define lenses in the obvious naive way using your ability to copy, so when I say lenses now I mean stochastic lenses. If you try to define stochastic lenses in the obvious naive way using this copy, this goes wrong. The resulting so-called category of lenses that you get fails to have an associative composition. So it's completely broken. It doesn't do what you want. And if you're unfortunate enough to read my PhD thesis, I mistakenly thought that this construction actually worked. I missed the part of the check where associativity was failing. So 4 years ago, I mistakenly thought that basically the definition I've already given you, in fact an earlier version that predated lenses, worked directly for probability as well. It turns out it doesn't, and you need quite a lot more machinery to deal with probability. So it turns out that although the definition of lenses that I've given doesn't work for stochastic processes, there is a more general definition that does work, and people call this optics. Optics is a generalization of lenses that works in a more general setting, and all of this was worked out by programmers for dealing with data. And it turns out that some very nice theory can basically just be imported directly. And this is going to be a proper generalization in the sense that if we have a monoidal category where the monoidal product actually is a Cartesian product, which means that we had the magical property that we need in order to define lenses, the definition of optics collapses back to the definition of lenses, or is equivalent. So this is a proper generalization. That being said, this is a highly non-obvious generalization. So let me draw a cone diagram. So if you remember a lens from x plus x minus to y plus y minus as a cone diagram looked like this. And now which of these colors has a chance of coming out? I'm not super optimistic about blue. Let's try this. I think orange was okay. Okay. So a generic lens as a cone diagram looks like this. You take the input, you take a copy, then you give the output of the forwards function, and then you store the copy and pull it across, and then you take the other input, and then you combine these by a function to give the final output. So this is the function from x plus to y plus. This goes from x plus times y minus to x minus. The appropriate generalization of this is, so an optic from x plus x minus to y plus y minus is going to consist of now a function. Okay, and now I just said function. A morphism in my monoidal category, and for this you can read a stochastic process. A stochastic process from x plus to a tensor product of y and something, and then another stochastic process from the something and the y minus to x minus. So this actually reintroduces the symmetry that we were missing before. And this wire here can live anywhere. This is some A. So one of these is actually, the data specifying this is a triple. So the data specifying one of these is a triple of an A, which is a set, or rather an object in my category, but in stochastic processes the objects are sets. Then a forwards function, which is, I keep saying function, a forwards morphism, which is going from x plus to the tensor product A times y plus, and then G, which is going from A times y minus to x x minus. Okay. And to figure out how to compose these things, we can basically read off the definition after doing my bigger fish composition. So if we have one of these given by F1 G1 like this, and then we have another one given by F2, G2, and this thing, this y carries an A and this y carries a B, and then you need to draw a big comb around this. So now the thing going across the top is a pair of wires, but remember that a pair of wires means a monoidal product. And in the category of stochastic processes, the monoidal product on the objects was the Cartesian product of sets. So what that means is that the data specifying the composite, the sequential composite here, we take the parameter here to be A times B. And then we can combine these, so we have something which needs to go from x, okay, let's call this x plus, y plus, z plus, z minus, y minus, x minus. So then we can get a function from x plus to stochastic process from x plus to A times B times z plus. Namely, I mean, you can just read it off here. So given an x, we get an A and a y plus, and then we take this y plus, and from that we get a B and a z plus. You have to do this kind of carefully this way, because the thing about stochastic processes is that now these outputs are no longer independent of each other. So these can be kind of statistically correlated. So this is like the example that I used to show that you can't freely copy in this category is the coin flip. So if you do a coin flip and then you copy it, you get these correlations. So this process could correlate these things. The reason that this is a proper generalization, so there's a super slick proof of this, which I don't really understand, which uses a result called the Ninja-Yone dilemma. But the intuitive idea is that so in the category of sets, a function from x plus to A times y plus always decomposes as a function from x plus to A and a function from x plus to y plus. So the category of sets and categories with this magical copying property have this property that a function into a product always decomposes as a product of functions, whereas in a properly monoidal category like stochastic processes, this is no longer the case. So what actually happens is in the category of sets, you can always replace this box with copying followed by something here and something here. And then what you do is you slide this box along this wire. So instead of putting it here, you put it over here. And then you consider the right-hand thing to be all of this. So you just put a box around that. So that's the intuitive proof that this is a proper generalization, that if we do this construction in the category of sets, we get back lenses or something equivalent to lenses by these manipulations. What I touched on there is that we need to be super careful if we're doing this properly, because these things are not literally triples like this. We need to impose an equivalence relation. In particular, hang on, let me reuse one of these diagrams here. Okay. we need to impose an equivalence relation which says that if our left thing actually looks like this, if it has some piece that lives just on this wire, it's the same as if this box was over here. So we need to impose an equivalent, and this, the act of doing that can change this, the set living in this wire. So we need to carefully impose an equivalence relation on these triples that says that these things are literally equal. So this is saying that we can't actually ever get at the set that this wire carries. We'll say it's not precisely pinned down. There are different equivalent ways of writing it, and fortunately, so this is very difficult. But fortunately, category theory comes gallantly to the rescue because this quotient that we need to take turns out to exactly be a certain thing called a coend, which is fairly well understood, and it actually has a lot of rules that make this behave like an integral. So we end up writing this in a notation which looks like integral A. So the set of these things, we write it as an integral A of stochastic processes from x plus to a tensor y plus times stochastic processes from a tensor y minus to x minus. And the reason that we do this, not just because it looks scary, but because you can manipulate these integrals by rules that look extremely familiar from calculus. In particular, the result I said, the Ninja-Yoneda lemma, which is what we use when we do this, collapse it back into the category of sets. This uses a rule that says that this does something like evaluating an integral at a Dirac measure, a point measure. So it says that if we evaluate an integral at a point measure, it's just the same as evaluating the function at that point. So we get a full integral calculus of these things, which is kind of fun. Okay. Now, so what can we do with this stuff? So in order to generalize open games from the category of sets to the category of stochastic processes, we actually have two problems. One is that we need to replace lenses with optics in order to get, so optics are the correct generalization of lenses for this setting, which is a monoidal category. The other thing is that we need to know how to change what a context is. So previously we had this thing where a context of an open game consisted of a lens into its source from nothing and a lens out of its target from nothing. So it behaves like this box into which you can slot an open game. The same idea works here, but again the details change. In particular, a context no longer separates into a pair consisting of a history and a continuation. And this is because, as a result of this correlations that can happen in this category, the context into which the open game is put can itself have some memory, that it can do some stuff before and then remember it. And this becomes significant in a way which it wasn't before. Precisely because players can now do Bayesian reasoning. So when players make an observation, they can then do Bayesian reasoning to learn something about the unobservable state of the game. So this is the new effect, the new game theoretic effect, which makes life difficult. So in order to fix this, we can do something which I also did before, which is to say that contexts are three-pronged combs. So here's our open game G from x plus x minus to y plus y minus. And a context is going to be a three-legged comb like this with ones on the outside. Now, at some point, I think 2 weeks ago, I fairly quickly hand-waved that if we take this principle that every output of this thing is a function of all of the inputs to the left of it, then you can derive from this HK pair, right? This thing decomposes as, this thing would decompose as, where should I put my orange? I need my orange. Oh, here it is. This thing would decompose as a H and a K. So this H goes here, K goes here, and then here you discard. So this symbol means throw away the value. In the stochastic setting, we can do basically the same reasoning, but at some point we used secretly one of the properties of sets. So the most general thing which one of these can be stochastically is a joint. So a triangle with two outputs is now a joint distribution. So call this A. So H is a joint distribution on x plus and A, and then K is a stochastic process from A and y plus to y minus. And then, so we still have some symmetry breaking here because in the category of stochastic processes, it's still the case that there is only one stochastic process into the one-element set, namely to discard. There's no other thing we can do. So if we're being fully symmetric, K would have to have two outputs, and then we'd have to have some triangle the other way. So if you're doing this in super generality, if you want to do this over relations, for example, you need a fully symmetrical setup like this. In stochastic processes, the only thing which this can be is discard and discard. And then, since K has this input which is only ever discarded, then we can do away with it. So implicitly, I'm still using some properties which are specific to the category of stochastic processes here. I'm not going to completely justify this, but intuitively I think this makes sense. So this context is going to consist of a joint state between the thing which the open game can observe and something else. And this A is the something else. This is like the unobservable state of the game. And then K, the continuation, is now also allowed to depend on this unknown state. So similarly to how over here I said if you do this construction over set, you can split this function up and then pull it through. You can do the same thing here. So in set, a joint state, the thing which would be a joint state in the category of sets, is just a pair. It's just an element of x plus times a, which is the same thing as an element of x plus and an element of a. So this thing decomposes into two parts, and then you can just pull this one through and absorb it into k. So the same reasoning holds. So it turns out that this is the correct definition of a context of an open game in the Bayesian setting. And so this carries around exactly as much information as you need to talk about the Bayesian updating, the learning that players can do. So because what you end up getting is that this thing ends up behaving like a common knowledge prior. So back to game theory, we still, I guess I didn't say this before, I really should have said this actually. Open games before have the property that the diagram that we draw, the structure of the game, is common knowledge to the players. So this is the same thing that you normally get in classical game theory, that the rules of the game, the rules of the game are common knowledge. We get the same thing here. So this H is really part of the game. So this ends up behaving like a common prior. So then some particular player then observes something about this x plus, and then they will do Bayesian reasoning, Bayesian updating to get a posterior distribution on the A, which they then, using this posterior distribution, they get a posterior K. So given this allows them to get a distribution on y minus given some particular choice. Yeah, the details get very nasty, but you can see we get this kind of correspondence between game theoretic reasoning and what the category theory and the diagrams give us. I actually, because I said so little, and I have these diagrams as a magic tool, I actually went faster than I was planning through this stuff. So using this, okay, so now I should give some examples. So to derive the sequential composition of these things, you can do this. You can essentially read off the definition of sequential composition by drawing diagrams like this. So imagine we have a G and an H arranged sequentially. Maybe I should draw this because this is not so clear. What I should say is the actual definition of an open game in the Bayesian setting is, now we've set up all of the pieces, is identical to before. So an open game from x plus x minus to y plus y minus consists of three things. One is a set of strategy profiles. One is a function that says for any strategy profile, you get an optic from x plus x minus to y plus y minus, which is an equivalence class of triples. And the third thing is a relation between the set of strategy profiles and the set of contexts. And again, the set of contexts is a set of equivalence classes, because you can do this sliding. So at the top level, the structure is identical. We've just replaced each of the pieces that it's made of with an appropriate generalization. Now, suppose in a string diagram, we're going to do some GH as a comb diagram. This corresponds to bigger fish composition. So we have GH, Now we put this game in a context. So this context is a three-legged comb like this. I've lost my orange again. This is terrible. It's up here. And now, so I'm going to hand wave here to give you an idea of how this construction works. Suppose we want to define the equilibrium relation of this sequential composite GH. So we're given strategy profiles to both of them, and we're given a context, and now we need to project this context to, or specialize this context to each component's viewpoint on it. So just like before, we're going to, so let's say we want to make G's view of this context. So just like before, we're going to specialize H by taking, so previously we took the lens which is indexed by tau, the strategy profile that we're playing. Now this is an optic, so this is some thing that looks like this. And then we know that the outer context also, so this is some A. So yeah. And then the outer context looks like something like this. Like this. And then we want to know what is the context from G's point of view. And now we just draw a big three-legged comb around all of this. And then we can just read off what should this be. And then we can do exactly the same thing to get H's thing. So this is a magical method to both discover what are the correct definitions, and also it really helps for proving the things that you need to prove to show that this is a monoidal category and so forth. Because you need to show, for example, that this thing is independent of the choice of equivalence classes. But you can argue this by sliding things around this diagram, which is very nice. Okay, so you can do a similar thing for the tensor product, which I think I'll say nothing at all about.
Is it possible in order to write the tensor product in terms of this graphical notation as it comes?
It is. Okay, yeah, okay, maybe I should say this, because actually it's kind of cool. This has a caveat that this is relying on a part of the graphical language which looks like it works, but I don't have this is a kind of, you take the graphical language and you just run with it. And at some point you lose track of the underlying meaning. So in order to do monoidal products, think about the particular three-legged comb given by a circuit diagram like this. That's not right. So I want to okay, now imagine I put a box here and a box here and stare at the wires. This thing is kind of implementing putting these two boxes in parallel. So if you if you follow the wires, you can see that if you then erase the outer shapes, you can pull these into parallel with each other. And the thing about this is that this doesn't just work on simple boxes like this, but if you do two of them, So this is going to be identical. Like this. And now, if I have a pair of combs, one going between, hang on, how do I want to do this? The planarity of this is actually a particularly subtle point, but I'm going to draw these non-planar. These do not have to be planar. It's aesthetically pleasant to make them planar. Yeah, okay. So we have a comb here and a comb here. And if I've got this right, this arrangement of them kind of implements doing these two in parallel. So you can do monoidal products this way, with the caveat that you can't technically prove things like this, because technically I can't really justify what these kind of things mean. I'm kind of working on this, or at least thinking about it, but it's not clear whether this actually saves effort versus... So for sure this is cleaner. This is a very slick looking way to do it, but I'm not sure by the time you have to deal with all the combinatorics of how these things can mesh with each other, I'm not sure this saves effort over just doing it the hard way. Yeah. So the answer to the question, can you do the monoidal product using combs, is sort of. Yes, with a caveat. Okay. So we have, after some serious hand waving, we have a monoidal category of open games, Bayesian open games, so we can continue to draw circuit diagrams. Then we can forget about combs and go back to drawing string diagrams like before. So to be clear, so there's a kind of separation actually in the uses of these two types of diagrams here. So these things are called string diagrams. So things where we draw, I've mostly been calling them circuit diagrams. Things where we draw circuit diagrams of games are useful for drawing pictures of actual specific games. Yeah, if you want to draw a specific 5-stage game or whatever, this is a fairly convenient language for doing that. The combs are a theoretical tool, in my opinion. Other people might think different and think that this is an intuitive way of drawing pictures of games. But I find, for drawing pictures of games, I find this more intuitive. But for spelunking inside the theory, for going into the foundations of compositional game theory, I find this a more convenient language. To an extent, these things are interchangeable. You can go back and forth every... well, yeah, to an extent. So every box here becomes a 2-legged comb here. Every 3-legged comb here becomes a 2-legged comb over here. So this ends up being this context that we draw around this game. So to a large extent, these are interchangeable. So in this language, we have forwards arrows and backwards arrows. In this language, everything goes forward, so we don't need to label our arrows because everything's always going from left to right. But the price that we pay is that these boxes become stretched out. What it means is that if we have a G at the beginning followed by lots of stuff, and then after the lots of stuff we get some payoff back, the comb for G becomes extremely long. It begins at the beginning and then it has to end at the end, and it has to kind of sit around the entire diagram. So in my opinion, these become quickly unwieldy to draw actual pictures of games in a way where this is convenient. Okay. Okay, so modulo a lot of hand waving, we have a monoidal category plus some other stuff. Everything that we need to justify drawing circuit diagrams for games like this. Then we need some generating families. Like before, we're going to have two generating families. One is, and actually they're going to be in exact one-to-one correspondence with the ones that we had before. We just need to fiddle with their definitions a bit. So we have the one-player open games and the zero-player open games. So again, we get a decision of y given an x from x1 to y reals. And okay, now the definition is going to be, so the sigma of this is going to be, I should be careful because now I'm using the letter D in two different ways. I've been using it for D for decision to denote a one-player open game, and I've also using it for here for this operator taking a set to its set of distributions on it. Finite support distributions. I didn't say that this week. Everything here is finite support. As long as you restrict all your sets being finite, it makes no difference. So I will upgrade this D to an A. There we go. So to make this clear. So the strategy profiles for a one-player game are going to be all of the ways which you can choose a y given an x, but now we're not doing pure strategies, we're doing behavioral strategies. So the behavioral strategies for this are a distribution on y for every x. Keep in mind that this is not, the set of mixed strategies is the set of mixtures of pure strategies. So we do, so you can, which way round can you do this? You can map this into this, but in general not the other way round. Yeah. These are related but different. Okay, we need a, given one of these, we need to get an optic like this, and it turns out to be basically as trivial as before. We have an isomorphism, but now it's not so obvious. So given some f from, so f is an element of this. We need to get an optic from x1 to y reals, and so an optic is a triple, and I'm going to take the stored set to be the one element set, and then up to some isomorphisms, the forwards thing is f and the backwards thing is discard. And this will be clearer if I draw a comb diagram for it. So we have x, y, reals, nothing. And the diagram that we draw is this. So for the thing across the top, we have empty space. And this means the monodal unit, which is the one element set. Okay. Now, for the third thing, what are the equilibria? Well, when is some f in equilibrium given a context? So, and this context okay, now a lot of this is 1, so on the outside of the context we have 1s always. So this needs to be the right shape so that we can insert this into it. So this here is also 1, so this entire right leg is completely trivial. And then we have reals, and then we have x, and we have y. Now the contexts of this can have this form. So this is triples consisting of h and a k related by some set A. And so A, H, K, like this. And then we need to define this. Now this ends up being something that I haven't set up any notation for. Roughly what we want this to be is that f, so after we observe, given this context, several things can happen because we make an observation of, so remember now this is one player, so we have this stochastic process coming in and the player observes it, so the player is actually making an observation of a random variable here. And we need to account for all of the different things that the player could observe. So the player makes some observation of this random variable. And this distribution here is common knowledge. Or just to say, we have one player here, so the player knows it. Then what the player is going to do is they're going to Bayesian update this joint distribution using the observation of x that they made. So they're going to get a posterior distribution on A. Now, so the player has, before they've made a decision, the player makes the observation, then they calculate the posterior on A. Now they have to make a decision. So now for every decision, for every okay, so in general they're going to play some mixed strategy of y, or some mixture of y. They're going to play a y probabilistically. So if they play some distribution of y, they know the posterior on A. These things are now independent because because the player is now choosing this. This is now like it's being controlled. Given these two things, we get a posterior distribution on the reals, and then we can take an expectation of that. This is the process we need to go through. So this will be an equilibrium precisely when, so this is something like f, and I'm going to heavily abuse notation here because I haven't set any up. So f of h marginalized to x. So this is a distribution on, no, this is wrong, this is wrong. I want to say for every x in the support of the right marginal, the x marginal of h. So this is for every observation that the player could make. I want that f of x. So f is a function from x of distributions on y. So the distribution on y that we get should be in the argmax of all distributions, and actually we can do a linearity argument and reduce this argmax to only searching over pure strategies now. But in any case, the argmax over all distributions on y of the expectation of k given beta and h right marginal, or the a marginal, given x. And now I'm using this bar for both Bayesian updating and also for marginalizing, which is bad, but okay, this and this are different. Okay, that ends up giving us a definition. We still have to argue that this thing is independent of the choice of equivalence classes. So we're not out of the woods. We still have to do some work here. Fortunately, it works. Okay, so that gives us our first generating family of open games. The second generating family is going to be the zero-player things, which are going to be precisely the optics lifted in the same way as before. So we take sigma to be the one element set, and we take E to be the always true relation. So that ends up also being exactly the same. So again, things look the same. We just have to very carefully switch out each piece for a corresponding generalization. You can, if you want, you can kind of try to axiomatize what does it mean to Bayesian update, and then say what does it mean to Bayesian update in the category of sets, and then it ends up completely trivializing, and you get back to what you had before. The other thing you have to do here is, oh no, this is okay because I'm quantifying over the support, so you never have to worry about zero distribution events, zero probability events. Is it okay if I run 5 more minutes? Yeah. Okay. So now we have 2 generating families, and we have 2 composition operators, and we also have to check that the language, the circuit diagram language of optics basically looks the same as the one that we had for lenses, but fortunately it basically does. So in the end, we basically get to draw exactly the same kind of diagrams as we had before, but now they're denoting Bayesian games rather than simple deterministic games, which means that we get to draw mixed states, priors, this kind of thing. So after an epic amount of work, you get to draw pictures like a normal form Bayesian game would look something like this. That would have some. So in a normal form Bayesian game, you'll have players choosing simultaneously, and they will have a type, and nature is drawing the types from some joint distribution, which is common knowledge. So so we're going to have some setting where the payoff of, so a player observes their own type. So this is type 1, this is type 2. So every player can have a behavioral strategy which tells them which choice to make given their type. And And their payoff is a function of both their choice and their type. So this is a very flexible setting. You can do a lot of interesting stuff in a setting like this. You probably want to specify that a player's payoff only depends on their own type, not on the type of the other player. So you can open this box, copy some more stuff and do that. If we had the thing which I was in the process of drawing by accident, which is that the payoffs only depend on the player's choices, not on their types, this ends up giving correlated equilibrium. Because correlated equilibrium is a special case of Bayesian Nash equilibrium, where the payoff function is not dependent on these types. So these end up now being signals. We can also draw the same thing but sequential. So okay, forwards, and then we have some payoff function, and I still need to take copies here and here, and then, okay, you have to be a bit careful drawing these, otherwise the number of wires and crossings gets out of hand very quickly, but this is a perfect information game with Bayesian types. So we have a joint distribution on the types, both players know their type, but now player 2 is additionally observing the move of player 1, and now you can have signaling effects where player 2's move signals information about their type. So things get, this is a fairly flexible setting. So this allows you to start to move away from everything being super common knowledge by the Harzani trick, although it's still basically impossible to move away from the prior being common knowledge. So that's the state of the art. So what we end up getting if we did all the hard work is that the equilibrium conditions you end up getting out are this thing called weak Bayesian. There's two parallel naming schemes in use, so we get this thing which is Bayesian Nash or weak Bayesian Nash. So which basically means that every player does Bayesian updating essentially once. So you don't have continuous learning. Players do Bayesian updating once, starting from a common knowledge prior. So there's also a strong Bayesian Nash, which is also called something else, where you have explicit belief systems and updating your beliefs. We can't get that. Possibly you could. I'm not sure. But this is the setting that we get. It's yeah. Okay, I've scrambled to the end. This is time to stop.